If you and your friend only moves in one direction, called the x direction, and the distance between is 16 meters, then this vector is one-dimensional with the magnitude of 16 meters in x direction. But now another dimension is opened and your friend is free to move in one more dimension. We call this new direction as the y direction. This time the distance between you and your friend is the combination of how much he moves in x direction and the y direction. And the vector it forms, we call it the two-dimensional vector, which is the combination of 16 meters magnitude in both x and y direction. But somehow your friend gets wings through which it can fly in straight up direction. We call it the z direction, which makes our new vector as a three-dimensional vector, which is the combination of magnitudes 16, 16 and 5 meters in x, y and z direction. And that's how we define vectors.
LiDAR, or light detection and ranging, is a tool used to quickly, accurately, and densely measure 3D features from the world around us. LiDAR sensors can take hundreds of thousands of measurements each second and are represented in the form of a point cloud. The point cloud can be used in various analytical processes to take distance measurements, compute volumes, and model objects in 3 dimensions. LiDAR is an active remote sensing system, meaning that the LiDAR system itself actively generates laser pulses used to take the measurements. These laser pulses are pulses of light that travel from the sensor to the ground and reflect off of things like buildings and tree branches. The reflected signal then returns to the LiDAR sensor where it is recorded and stored as a distance. LiDAR data can be used to estimate tree height, measure power line sag, detect changes in topography from one date to another, and numerous other applications. Phoenix LiDAR Systems is dedicated to making and sharing high-quality content on this channel. If you have any questions for us, be sure to leave them in the comments section below. Thanks for watching, and we will see you next time.
Have you ever wondered why soccer balls are made up of pentagons and hexagons? It's actually really important because if they were only made up of pentagons, it wouldn't be a ball, but rather a dodecahedron. The addition of hexagons allows the shapes to fit together like a puzzle and form the perfectly spherical shape that we all know and love.
Ever since pool or billiards has existed,
Inflation, RPI and CPI. Inflation measures how much more expensive a set of goods and services has become over a certain period, usually a year. It represents the change in the price of goods and services we buy. The annual rate of inflation shows how much higher or lower prices are compared with the same month a year earlier. It indicates changes to our cost of living. This graph shows the level of inflation in the UK between 1960 and 2022. You can see that there was a period of very high inflation in the 1970s. This was caused by a series of economic shocks culminated in the oil crisis of 1973. Inflation has also started to rise again recently. There are two main measures of inflation in the UK: the Consumer Price Index and the Retail Price Index. The figures are compiled by the Office for National Statistics. The inflation rate is calculated every month by looking at the changes in prices of goods and services. The prices are looked at in over 100 different areas across the UK so that regional differences can be taken into account. The items included in the calculations are known as the basket of goods. The basket of goods is designed to reflect everyday typical things that people buy. There are around 700 separate items in the basket, under groups such as food, clothing, furniture, and household utilities. The basket of goods is regularly updated to reflect changes in the things we buy. Some things that have recently been taken out are hand hygiene gel, hot rotisserie cooked chicken, and bakeware. Some recent additions are air fryer, vinyl music, gluten-free bread, and edible sunflower seeds. The CPI and RPI are in effect two different baskets. Amongst the biggest differences is that RPI includes housing costs such as mortgage interest payments and council tax, whereas CPI does not. Although the Retail Price Index is a long-standing measure of inflation, it no longer meets the requirements to be designated a national statistic. Inflation indices are tables of numbers that represent inflation. These can be based off the CPI or the RPI. There is always a base year where the value is 100. The numbers either side of the base year show the relative inflation. In 2016, the index is 120, so the prices were 20% more than in 2015. Another way to say this is that they were 1.2 times more. In 2017, the index shows us that prices were 50% more than in 2015. Or we could say they were multiplied by 1.5. If we are going from the base year, then the multipliers are easier to see, as we are always starting with 100. However, we can see the inflation between any 2 years by finding out the multiplier. For example, if we wanted to know how much more expensive goods were in 2017 compared to 2016, we want to know how you get from 120 to 150. We can work this out by performing a division calculation. 150 divided by 120 is 1.25. Sometimes the information is presented to you in a graph. The information is exactly the same, except you have to read off the graph to obtain the value. Let's look at a question together. Part A asks us if a food item cost £3.80 in 2016, how much would we expect to pay for it in 2017? We already know the multiplier between 2016 and 2017, so we use this with price. 3.8 multiplied by 1.25 is 4.75, so the item would have cost £4.75 in 2017. Part B asks us, if an electrical item cost £260 in 2017, how much would it have cost in 2060? This part of the question is a little bit different as we are working backwards. We already have the multiplier, but we just need to perform the opposite operation and divide instead of multiply. So 260 divided by 1.25 is 208. The item would have cost £208 in 2016.
To getting the disease, those who are infectious, and then those who have recovered from the infection. So people who are immune don't play into it. The way I've written these, for every unit of time that a susceptible person spends within a certain infection radius of someone with the disease, they'll have some probability of contracting it themselves. So we're using physical proximity as a stand-in for things like shaking hands, touching the same surface, kissing, sneezing on each other, all that good stuff. Then, for each infectious person, after some amount of time, they'll recover and no longer be able to spread the disease. Or if they die, they also won't be able to spread it anymore. So as a more generic term, sometimes people consider the R in SIR to stand for removed. This should go without saying, but let me emphasize it at the start anyway. These are toy models, with a tiny population, inevitably falling far short of the complexities in real people and larger populations. I am not an epidemiologist, so I would be very hesitant to generalize any of the lessons here without deeper consideration. That said, I think it can be healthy to engage the little scientist inside all of us and take the chance to be experimental and quantitative, even if it's in a necessarily limited fashion, especially if the alternative is to dwell on headlines and uncertainty. We'll start things simple and layer on more complexity gradually. In these first few runs that you're looking at, everybody is simply meandering around the city in a kind of random walk, and the infection follows the rules that we've laid out. So, it doesn't look great. After not too long, almost everybody gets infected. As a sanity check, what would you expect to happen if I double this radius of infection? You might think of this as representing more total interactions between people, or a more socially engaged society. It'll spread more quickly, of course, but how much? It's actually very drastic. Within a short time span, the majority of our little population is infected simultaneously. As another sanity check, what would you expect if we go back to the original infection radius and then we cut the probability of infection in half? Remember, the way this is running, for each day that a susceptible person is within that radius of an infectious person, they have some probability of becoming infected. By default, I've set it to 20%, but this is the number that we're now going to cut in half. You might think of this as better hand washing, better cough protection, and less face touching. As you might expect, it spreads out the curve. In fact, it does this by quite a lot, which really illustrates how changes to hygiene have very large effects on the rate of spreading. The first of several key takeaways here that I'd like you to tuck away in your mind is just how sensitive this growth can be to each parameter in our control. It's not that hard to imagine changing your daily habits in a way that multiplies the number of people you interact with, or that cuts your probability of catching an infection in half. But the implications for the pace of the spread are huge. The goal is probably to reduce the total number of people who die, which is going to be some proportion of this removed category in the end. That proportion is not a constant, though. If you get to a point where the peak of the infection curve is too high, meaning there's a time when many people are all sick at once, that's the point when available healthcare resources are overwhelmed, which, for a bad disease, will increase the mortality rate. Now, I don't know where you're from, but in most towns, people don't actually spend their days drunkenly wandering around the city like this. Often there's a common destination, like a central market or a school. In our model, if we introduce some central spot like this that people regularly visit and then return from, it's, well, just look. One of the main things I was curious about is how to mitigate this effect, and that's something we'll examine in just a bit. Another feature that we could include is to have a few separate communities with transit between them. Every day, each person will have some probability of traveling to the center of another community and then going about their usual routine from there. All of that is our basic setup, so now the question is, what actions help to stop this spread? What is by far most effective is to identify.
I'm going to show you how to play Crowded Rectangles. This is a 2-player game, and you will need one printed game board that looks like this. It's just basically a big square grid. You need 2 dice and 2 different colored markers. So the first player will roll. They got a 3 and a 4. So we'll say that's player blue. They're going to make a rectangle that has 3 squares down and 4 squares across. And they're going to write the multiplication problem, 3 times 4. Now, if you make a rectangle and you don't know the answer to your multiplication problem, you can just count the squares. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So then the next player will go, and pink got 3 times 4. That's funny, they got 3 times 4 too. Okay, let's make another one just like that. 3 times 4 equals 12. So we're tied so far. Here's a 4 times 5. 1, 2, 3, 4. 1, 2, 3, 4, 5. So we'll do 4 times 5 equals 20, and this board is filling up fast. Here's a 4 times 2 from pink. We can fit that right in here. 4 times 2 equals 8. And what we're doing is we're filling in all of the squares of this board. In a little bit, somebody will roll and won't be able to fit their rectangle inside the board. When that happens, the game ends. So let's see what happens next. Oh, we're rolling some big ones. 5 times 4 is 20 again. Five times 4 equals 20. Let's see if pink can get a big one. 3 times 6 is 18. Let's see here. Let's do 1, 2, 3. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. There's not much board left. 3 times 6 equals 18. Let's see if blue can fit anything in here. 5 times 3 is not going to fit there, so our game ends right there, and now we just need to add up the points. So pink has 12 plus 18 plus 8. That's 38. And blue has 12 plus 20 plus 20, which is 52. So blue wins that game. And that's how you play Crowded Rectangles.